Hi everybody, welcome back. So where we left off last time is we were talking about the impact that a good leaving group can have on an SN1E1 reaction relative to an SN2E2 reaction. Specifically, that the strength of leaving groups, so in other words, how weak of a base is our leaving group, has a bigger effect on SN1E1 reactions than SN2E2. Simply for the fact that in SN1E1 reactions, the leaving group has to leave all by itself. And so what I'd like to talk about now is to give you a little bit more information about leaving groups. And so we've talked previously that leaving groups are the kind of thing that when they leave, they take the electrons with them. And so what I've drawn out here is a very general reaction where we've got R, so a carbon containing something or other, is bound to Y, a leaving group with a formal charge of N. And so in the case of like bromide, chloride, iodide as a leaving group, your initial formal charge would be 0. Through heterolysis, so in other words, we're going to lose our leaving group by taking the electrons and giving them to the leaving group species. We're going to generate a carbocation plus a leaving group, which now has a formal charge that is 1 less than the formal charge which we started with. And so what we can do is we can actually create a leaving group series. So essentially a series that shows us from really, really bad leaving groups to really, really good leaving groups, just to give you an idea of sort of the entire span of leaving group ability, rather than just relying on the adage, a good leaving group is a weak base. Because keep in mind, weak base is not necessarily a monolithic concept. It has a spectrum associated with it. So our series here starts with hydride and CH3-. You can think about this as that these are, by all definitions, not a weak base. So H- or CH3- is incredibly strong base, which means that as a leaving group, they're very unstable or high energy. And so on this spectrum, I like to classify these as a nope, not gonna happen types of leaving groups. And so if you're tempted to draw arrows which show H- or CH3- leaving from a carbon-containing group, think again. This is simply such a high energy process that this doesn't wind up happening. So these are much worse than what we consider our poor leaving groups. So things like NH2-, OH-, or RO-, so an alkoxide. These are not great leaving groups either, but they're to the point where you can actually form these suckers in solution. So specifically, can you make NH2 leave? Yes. Is it tough? You betcha. And so these poor leaving groups, while they certainly are capable of functioning as a leaving group, most often, if there's another opportunity for something to act as a leaving group, it will wind up doing so. So next, in this series of leaving groups, we've got fluoride, carboxylate, so the conjugate base of like acetic acid, and chloride. So we typically have, up until this point, lumped all halogens together as good leaving groups. This really isn't the case. And so to be a really good leaving group, you have to be an incredibly weak base. And so while chloride is certainly a weak base, it's really not weak enough to function as a leaving group where this is going to want to leave of its own volition. And so that being said, when we make our leaving groups sort of have bigger orbitals to better stabilize the added electrons of the charge, which they're taking up here, so by basically taking these electrons and donating them onto the leaving group, things like bromide are much better at leaving than things like chloride. Additionally, we can also essentially make our formal charge such that we're leaving something without extra electrons. So in the case of water here, we would start off with what we call an oxonium ion, so R bound to OH2+, meaning that water, which in and of itself is a weak base, is able to leave. The same thing with an alcohol here. Iodide and then triflate, so the basically trifluoromethyl substituted version of sulfuric acid, wind up showing us our great leaving groups here. And so what we can think about is that SN1 and E1 reactions, because we have to have the leaving group leave all by itself, they need a great leaving group. So in order to have an SN1 or E1 reaction occur with an appreciable rate, so a rate where you can actually track it, you're going to need something like bromide, you're going to need something like iodide, or you're going to need something like triflate. Otherwise, this reaction is going to be slowed to the point where you're simply not going to see product. On the other hand, SN2 and E2, we can use these okay, or even in some cases poor leaving groups because we have that assist in breaking that carbon leaving group bond. Specifically, we're using a lone pair of electrons, or a pair of electrons, potentially like in a pi bond, as a nucleophile to overlap with the anti-bonding orbital between the carbon and the leaving group. This assists in breaking a bond and makes poor leaving groups possible in an SN2E2 reaction. Again, as I mentioned in the last video, this doesn't mean that they're going to happen well, and it doesn't mean that this reaction is going to happen with an appreciable rate. And so typically, there are better ways to control a reaction than simply using a poor leaving group to make it SN2 or E2. But keep in mind, if something is not really this great leaving group, your ability to do SN1 is severely hampered. Okay, so what I'm going to do is I'm going to step out of the screen. I'd like you to go ahead and pause this so that you're able to write all of this on your paper. And then when you're done, restart the video and we'll talk about, so what do you do if you have a bad leaving group? Welcome back. So what do you do when you have a bad leaving group? It turns out we can't all have bromides and iodides all the time as our leaving group. Sometimes we're going to wind up with things like ethers or alcohols. And you can either let this get you down, or you can change the leaving group into something better. And so in this case, OHs and OR groups, yes, technically they are leaving groups, but you'll see that while we are generating a carbocation here, the leaving group that we are spitting out is a high energy species. So these are strong bases, meaning that they're not very stable. The easiest way to convert these bad leaving groups into a good leaving group is through the addition of a proton. So for example, if you simply add an acid to an alcohol, and so this usually requires a really strong acid, so something where a pK is less than 0, we're able to protonate the oxygen of the alcohol and form what's called an oxonium ion here. This means that water is able to function as our leaving group. Because remember, when we have a leaving group leave, we decrease the formal charge by 1. So if our formal charge is positive here, when it leaves, it will be neutral. And in doing this, we're going to create a carbocation, which is high energy, but in this case, our leaving group here is happy as a clam to exist as is. We can do the exact same thing for an ether. If we protonate the oxygen of the ether, we again form this oxonium ion, which is just an oxygen with 3 bonds. This is very similar to the hydronium ion we learned about in Gen Chem 2. Oxonium simply refers to an ion like this where one of the substituents is carbon in nature. This allows the loss of an alcohol as a neutral species and the production of the carbocation. And this allows this to happen at a much quicker rate than it would be if we simply mixed something like an alcohol, if we mixed an ether in a solvent such as an alcohol. Okay, so let's take an example of this. Let's say we wanted to go ahead and run a reaction between methoxybenzene here and sodium iodide. And so this SN2 reaction would be such that we would take the lone pair on iodine, run a backside attack on this sp3 hybridized carbon. Remember, in order to have SN2 be effective, this has to be an sp3 hybridized carbon bound to a leaving group. And this would wind up forming methyl iodide and the phenolate anion, which has a counterion of sodium plus. It turns out, though, that this leaving group here is really kind of terrible. OH minus is a strong base. Excuse me, the phenoxide anion here is a strong base, and so it's not going to want to leave. And so if we mix these together, there is no appreciable reaction. And so that being said, this doesn't mean that we simply can't wind up producing product here. So instead of adding sodium iodide as your source of I- nucleophile, what chemists can do is they can add hydriodic acid, so HI. This will perform a 2-step reaction, the first of which is a proton transfer. So we're going to move a proton from the hydriodic acid to the most basic position on our ether, which is the lone pair of electrons, and we'll produce an oxonium ion. So just remember, pH is just the lazy chemist's abbreviation for phenyl, or a benzene ring here. So at this point now, we have a really good leaving group. So what we're able to do is we're able to take the iodide, I-, which was produced upon the deprotonation of hydriodic acid, that's able to come in and perform backside attack on our oxonium ion, giving us our product phenol and iodomethane. So the take-home point of this is that just because you have a poor leaving group, remember that chemical transformations such as a proton transfer exist to turn this poor leaving group into a great leaving group. Okay, so this is the end of this video. Where we're going to pick up next time is how does the nature of an electrophile, so whether it's a primary electrophile, secondary, or tertiary with respect to the carbon leaving group bond, how does that affect what type of substitution or elimination that we're able to do? See you soon.